Okay, well these are section 2 problems I'm having to re-record, but I've already have the stuff worked out, so I'm not going to rewrite everything. So it might go a little faster, so you may have to pause it if you want to copy things down. Anyway, this is problem 13, and we're trying to find whether Rawls' theorem applies and whether to prove it applies. So the requirements for Rawls' theorem to apply are that the function is continuous, which it is because it's a polynomial if you multiply all that stuff out, and also that the value of the function at the beginning of the interval equals the value of the function at the end of the interval. So if you plug in f of 1, you'll see this term goes to 0, and if you plug in plug in 3, this one will go to 0. So they're both equal to 0. You could plug that in, but you'll find out this one's 0 and this one's 0 for the two cases. So that's true. The function is equal to each. The beginning of the interval is equal to the function at the end of the interval. Now I'm going to just go ahead and multiply this out. So if you do these first two terms using FOIL, you'll get that. And then you have the third term. Then you multiply it out. You'll have 6 terms. X squared times that, this times that, does it. So you have x times each one of these, x times each one of those, and you have negative 3 times each one of those, which gives you this equation. So x times x squared is x cubed, and so forth and so on. And then we combine like terms to come up with our equation. So this is equivalent to this equation. This is the factored form. This is the original form. So Rawls' theorem says if this is true and the function is continuous, which it is because it's a polynomial, then there should be some value of x between 1 and 3 where this derivative is equal to 0. So we take the derivative of this expression, and you get 3x squared minus 12x plus 11. And you set that equal to 0 and factor it. So set that equal to 0. It looks hard at first, and you could use completing the square, but I think, is that what I do? Actually, that is what I do. Use completing the square. So I move 11 to the other side, so that becomes negative 11. Then I factor out of 3 for the first two terms, so that if you factor out of 3 from here, you get x squared, and if you factor out of 3 from there, you get negative 4. Then we take this coefficient, negative 4, which is the term multiplied by x. We take that, divide by 2, and square it. So that's negative 2 squared, which is 4. So we add 4 here to this inner term. And we don't just add 4 to the right-hand side because we're multiplying this whole thing by 3. So we take 3 times 4, which is 12, and we add that to both sides. Here we're doing it explicitly. Here we're kind of doing it implicitly by 3 times 4 is 12. So this can be collapsed into a perfect square because that's what happens when you go through this procedure and you use negative 2 as the factor in the perfect square. So you get 3 times x minus 2 quantity squared is equal to 12 minus 11, which is 1. Then we divide by 3, take the square root, and you get the solutions. There are 2 solutions. Okay, so we take the square root, and then we add 2 to both sides. So what we did here is 1, square root of 1 is 1. Square root of 3 is 3. So I just changed it to that. And we have the plus and minus because we took the square root. And then we add 2 to both sides. So these are our 2 values of x where the derivative equals 0. And one of these has to be between 1 and positive 3. Well, let's see. Which one are we going to do? Or maybe there's 2 of them. Because what is this? 1 divided by the square root of 3. Well, the square root of 3 is greater than 1. How do we know that? Well, because any number, square root of any number greater than 1 is going to be greater than 1. So the square root of 3 is greater than 1. Turns out to be 1.728. So this is going to be, this number is going to be less than 1. 1 divided by a number greater than 1 is less than 1. So we get 2 plus or minus that number. And so you actually get two cases. Here I'm finding a common denominator and just simplifying it. So this can be rewritten as this. How do we do that? Well, we multiply 2 by the square root of 3 divided by the square root of 3. So multiplying by 1 essentially. Then we have the 2. We have square root of 3, so we can put that in the denominator. Common denominator. Then we multiply both the numerator and the denominator by the square root of 3. That gives us a 3 in the denominator instead of the square root of 3. We always like to have the radicals in the numerator, but not in the denominator. Okay, so when you multiply that, you get 3, and square root of 3 times 3 is square root of 3 squared, which is going to be 3. So this thing becomes 3. 2 times 3 is 6. 1 times the square root of 3 is square root of 3. So we get 6 plus or minus 3 divided square root of 3 divided by 3. So those are my two values of x. And the question is, are they between 1 and 3? And as I said, both of them are. If you just carry this out, and I just went actually to, instead of using this version, I used this version. I don't know why, but I did. So actually what it did is 2 plus or minus the square root of 3 over 3. Because if you take this term and multiply by the square root of 3 over the square root of 3, just this term, you'll get 2 plus or minus the square root of 3 over 3. So that's what I used. And you get these two values of x, which are between 1 and 3, so therefore Rawls' theorem applies. We did have at least one value to C. In this case, we had two values, which is fine. Okay, this is problem 15. And so we're doing the same thing as problem 13. It's just we have a different function. So our function is x to the 2/3 minus 1. And we're looking between -8 and +8. So the first thing we do is we need to show that the value of the function at -8 is equal to the value of the function at 8. So -8 to the 2/3, well, if you take the cube root of -8, you'll get -2. -2 squared will be 4. So this becomes 4, +4 minus 1 is 3. Likewise, if you plug in +8, which is this, you get 8 to the 2/3, which is 4 minus 1, which is 3. So this is equal to that. This function is also continuous, and there are no cases where the function is not defined. So we're good there. Now we take the derivative. The derivative of -1 is 0, so we just take the derivative of x to the 2/3, which is 2/3 x to the -1/3, and you can move that x to the -1/3 into the denominator, so it becomes x to the +1/3. So the question is, are there any values where this function is 0 or undefined? Well, it's 0 nowhere because the numerator never goes to 0. It's undefined when x equals 0. So x equals 0 is a possible point where we have a maximum. But so actually that's a problem. Okay. So it said it had to be continuous and differentiable. Well, it's continuous. I think it has like a well, it doesn't have a cusp. We'll look at it in a second. It's not differentiable. Therefore, because it's not differentiable, Rawls' theorem does not apply. So we can't apply it. Let's just plot this function. So the function is x to the 2/3 power minus 1. And you can see that actually it only shows part of the function. It doesn't show, I think I know what I've got to do. I've got to take x to the 2/3, but I've got to what I could do is x squared and raise that to the 1/3 power. That's the same thing. So there you go. So at x equals 0, the function exists and the derivative exists. The derivative doesn't exist, but it's continuous, but it's not differentiable because the actual derivative, if we keep zooming in on this thing, it'll end up going to infinity, I think. Well, actually, it doesn't matter. The derivative is different on either side. So you've got a negative derivative and positive derivative. So the function exists, and the function doesn't go to infinity, but it does. You have a different derivative in either case, so that's why you can't do it. It's not differentiable. Okay, this is problem 20, still Rolle's theorem. So is the cosine of pi equal to the cosine of 0? Yes, the answer is yes. Of course, this is one full cycle, so you'd expect them to be the same. The cosine of 0 is 1, the cosine of 2 pi is 1. So that's true. Now we take the derivative, and the derivative of the cosine is negative the sine. So we take the derivative, f prime of x is negative the sine of x, and the question is the sine of x 0 between 0 and 2 pi? And the answer is yes. And you can just answer this by just doing the unit circle. Unit circle, the sine of the angle is the y coordinate on the circle. So the question is, does y go to 0 somewhere between 0 and 2 pi? So it's 0, 0, and it's 0 pi and then back to 2 pi again. So in this case, the other ones are on the ends of the intervals, but this one is in the middle, so theta equals pi. And so let's just plot that. So let me switch over here. Graphing program. So the function was the cosine of x. If I remember correctly, yes. So here it is, and so you can see that the value of the function is the same at the beginning and the end. It's equal to 1, and there is one point at x equals pi where the slope is also 0. The slope is 0 at the beginning and the end, but they're not talking about the ends of the interval. They're talking about there's at least one point, which is this point in the middle. Testing. Okay, so this is problem 24, which is the last one of the Rolle's theorem problems. So we're getting used to the drill here. So the question is, does the secant at negative pi over 4 equal to the secant of pi over 4? Well, remember the secant is the same as 1 over the cosine. So does the cosine of negative pi over 4 equal the cosine of pi over 4? The answer is yes, because you remember the shape of the cosine curve. It goes through 1 at x equals 0, and then goes down to 0 at negative pi over 2 and positive pi over 2. So it's a symmetric. It's called an even equation because it's the same on either side of the origin. So yes, that is true. So that's true, and the function is continuous. Well, it's continuous in this interval. So it's not continuous because it does have a vertical asymptote at negative pi over 2, positive pi over 2, and multiples of pi. So anyway, it is continuous in the interval that we're talking about. So anyway, actually, I think I did this wrong the first time. So I said here, not continuous or differentiable at negative pi over 2 and positive pi over 2, which is true, but that's not the point because it's in the interval. Oh, so I think I realized that later. Okay. So the derivative, so it's not continuous there, but again, that's not inside the interval, so we can continue on. So you take the derivative of the secant, and the derivative of the secant is the secant tangent from the table in the book. And we set that equal to 0, and we say, okay, when is this equal to 0? Well, it's equal to 0 when the secant equals 0 or when the tangent equals 0. Well, the secant never is equal to 0. Here's the graph of the secant. It has vertical asymptotes at negative pi over 2 and positive pi over 2, and its minimum value is 1. So it never goes to 0. So this part never goes to 0. But the tangent does go to 0. Here's my graph of the tangent. And here's negative pi over 2 and positive pi over 2. So you go from negative infinity through 0 up to positive infinity. And so at x equals 0, the tangent equals 0. So that is the value of x, where the derivative is equal to 0. And therefore, that is 1 point between negative pi over 4 and positive pi over 4, where the derivative is equal to 0. So therefore, Rolle's theorem applies in that case, and it's true. Okay, we're going to now do some mean value theorem problems. And the difference between the mean value theorem and the Rolle's theorem is that you don't have to have the function value equal to each other at the ends of the interval. You just have to have the function continuous and differentiable in the interval. Make sure that the definition says that it's continuous and differentiable on the open interval. So we have to find out whether it's differentiable and continuous from -2 to +1. And because we're just dealing with a polynomial, it's easy to make that judgment. It's a polynomial, so we take the derivative, and the derivative always exists. So the intermediate value theorem says that if you take the average slope between the beginning and the end points of the interval, so we do x equals -2 and whatever the y value is. And this is not x, y. This is the beginning of the interval and the end of the interval. So these are the two x values. So this is b and this is a, or this is a and this is b. It doesn't matter. I guess this would be a and this would be b. And then we find the value of the function. We calculate this value, this average slope, and there is some point between x equals -2 and x equals +1 where the average slope is equal to the actual derivative. So we're going to calculate this right-hand side by finding f of b and f of a. So f of b would be -2 squared, which is +4, and f of a is 1 squared, which is 1. So this is my x value, y value, x value, y value. Plug those in there, and you find out that according to the mean value theorem, there is some value between x equals -2 and x equals +1 where the slope is -1. So rather than setting the derivative equal to 0, we set the derivative equal to this and solve for the values of x. So we take the derivative of x squared, which is 2x, and then we set that equal to -1, this number. And then we solve for x, and we get x is -1/2. Is that between -2 and 1? The answer is yes, and therefore the mean value theorem is satisfied. We don't have to actually calculate what the y value is. That's immaterial. We just have to worry about this slope. And if we plot the function, here let's. So this is the function. This is the beginning of the interval, -2, 4. This is the end of the interval, 1, 1. So that's my average slope, and you can see I have this line which has the same slope as the average one, and you can see that there is a point right there when x equals -1/2 where the derivative of the function at that point is the same as the average slope between the beginning and the end of the interval. Okay, this is our next problem. So again, we're going to use the mean value theorem. So we're going to evaluate the function at the beginning, the end of the interval. So we're going to say A is 1/2, B is 2. So if we plug 1/2 into this equation, we get 3. So you get 1/2 plus 1 is 3/2 divided by 1/2 is 3. 2 plus 1 is 3 divided by 2 is 3/2. So that's the value of the function. Then we calculate the slope between these 2 points. So you take delta y over delta x. So this is delta y divided by delta x, and we get a slope of -1. So the mean value theorem says there's some value of x between 1/2 and 2 where the slope is equal to, or the derivative is equal to -1. So now we need to find that value to confirm that there is a point. So we take the original function, which I'm going to rewrite as 1 plus 1 over x. If we divide x by x, we get 1. Divide 1 divided by x, we get 1 over x. This is the same as x to the -1 power. So we take the derivative. This goes to 0. This becomes -1 over -1 times x to the -2 power. Then you can move that to the denominator. Okay, and then we set the derivative equal to this number, not to 0. So -1 over x squared is equal to -1, multiplied by x squared, multiplied by -1, and you'll get x squared is equal to 1. So we take the square root, and we get plus or minus 1. We don't have to worry about the -1 because that's not inside of our interval. But what that's saying is that at x equals +1, that slope should be equal to this -1 value here. And is that is +1 between 1/2 and 2? Yes. And I think I have a picture here. So here's the function. That's point A on the curve. This is point B on the curve. Draw a line between the two. That's the slope. Here's another line with the same slope. So I take this down. Where does the derivative equal -1? Right there. That's what value of x is that. X is equal to 1 at that point. That's what we just found out here. Okay, now we're looking at problem 58. And first this seems kind of crazy, but it's made exactly so that you can answer the question. So it says when an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. 5 hours later, the core temperature is 390 degrees Fahrenheit. Explain why there must exist a time in the interval where the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. So what we have is at 0 hours, the temperature is this. At 5 hours, the temperature is that. So the mean value theorem says that if you take the average slope of this line, which would be this minus that, divided by that minus that, or this minus that divided by that minus that, that there should be some point in that where that value is reached. In this particular, they're specifically asking for that. So if we take that, find that slope, plugging those numbers in, you get -222 degrees Fahrenheit per hour. And that's the number quoted in the problem. So the intermediate value theorem says that there's at least one point between 0 and 5 hours where this is true. So that's why it works. If we look at this curve, what it's saying is that this is what the curve actually looks like if you look at the physics of the situation. It starts at 1500. After 5 hours, it's 390. And as time goes to infinity, it's going to approach the room temperature, which is 90 degrees Fahrenheit. For our particular case, we have these 2 points, 5 hours, 390, 0 hours, 1500. You draw a line between the two. The slope of this line is some value, which is -222 degrees Fahrenheit. And if you clone that, it says that there is some point, in this case right there, where the says there is just a time in the interval, which is this time right there, this time where the temperature is decreasing exactly at a rate of 222 degrees Fahrenheit per hour. Here it's increasing at a greater rate. Here it's decreasing at a lesser rate. At this point exactly, it's increasing at the same as the average rate. Okay, problem 60 is very similar to problem 58. It's the same kind of thought process. This is at a time of 0 seconds. We're going to say 0 seconds is at 9:13 a.m. Time is 0 minutes. And 2 minutes later, which is 9:15, we're going to say the time is 2. And according to this, at 0 time, we have a speed of 35 miles per hour, and at this time of 2, we have 85 miles per hour. So if you take the average slope of those two, 85 minus this divided by 2 minus that, you'll get a number, and I don't know where my number is. Oh, here it is. So you take that and you get 1,500 miles per hour. Not sure why I have this, miles per hour squared. And so that's the average slope between these two. And it's saying here, prove that at some time during the 2-minute interval, the car's acceleration is exactly 1,500 miles per hour squared. So this is the average value. So just in the same theories before, if we take the average value, which is this slope, and we clone it, this is the average change in velocity divided by the time. It's actually the change in velocity divided by the difference in time. This is the average value. You can say no matter how the car accelerates, if it accelerates slowly and then does most of the acceleration at the end, or it accelerates faster at the beginning and then slows down, or it actually even goes faster than 85 miles per hour and comes down. Each one of these has a point in the interval from 0 to 2 seconds where the slope is exactly equal to the average slope between the beginning and the end. So it's again using the mean value theorem to prove this is true.